let's wrap up today's lecture. And this is the last video. So let's look at a second order circuit. It's a second order bandpass. And we can design a second order bandpass. And this one does require an inductor. It's possible to design a second order bandpass using only resistors and capacitors if you use an active filter, one that uses op amps. So R, L, and C, and this is the input voltage, this is the output voltage. So let's talk briefly about how this works. At low frequencies, our capacitor is an open, our inductor is a short, so there's no current in the circuit, so there'd be no output voltage, no IR drop, no voltage across the resistor. The current would be zero, so the output voltage would be zero. At high frequencies, it's the inductor that acts like an open circuit. It has an impedance of j omega L, and as omega increases, that impedance approaches infinity, and the capacitor then acts like a short circuit, 1 over j omega C. But again, since the inductor is now an open at high frequencies, there's no current, there's no output voltage. There exists a particular frequency at which the magnitude of j omega L is equal to the magnitude of 1 over j omega C. The impedance, remember here, we could usually write this as j omega L, and then the impedance of the capacitor is minus j over omega C. So there's a particular frequency at which these impedances are equal in magnitude but opposite in sign. And so together, these two, ZL plus ZC, act like a short circuit at that particular frequency. It's called the resonant frequency of the circuit, and we call that omega 0. But at that frequency, this is a short circuit, and the output voltage would be equal to the input voltage. So it's going to have this classic bandpass shape. As a matter of fact, the response would look on a dB scale, and it's going to look like this. There's a particular frequency, the resonant frequency, omega 0, and then the bandpass response looks something like this. It's going to fall off. It's going to increase for frequencies below omega 0. It's going to increase at 20 dB per decade, and for frequencies above omega 0, it's going to decrease at 20 dB per decade. There's our 0.707. If you take 20 log of 0.707, it turns out to be minus 3 dB. So the two frequencies at which the response is down by 3 dB from the peak response are called our corner frequencies or cutoff frequencies. And so this is going to be the transfer function or frequency response of this particular circuit in a Bode magnitude plot. In a linear plot, it's actually going to look more like this, where this is omega 0. It would have a peak response of 1 and go to 0, okay, as a function of omega. Okay. So if you go through the analysis of this circuit, you can put it in the form. You just want to do this once. 2, and then this is a Greek letter psi. I'm sorry, C is how it's pronounced typically. And then in the denominator 1 plus j 2 C omega over omega 0, and then plus j omega over omega 0 squared. Notice I could have this j squared, which would be minus 1, so I could write this as minus omega over omega 0 squared, but it's often written in this form. So this would you can write the transfer function in this form, where omega 0, the resonant frequency, turns out to be 1 over the square root of LC, and then this C parameter is R over 2 times the square root of C over L. Now typically we don't specify the filter in terms of C and omega 0. Instead, we typically define the filter in terms of its desired bandwidth, the distance between omega C and omega C2 and omega C1, and the resonant frequency, or what's often called the center frequency of the bandpass filter. So we want to come up with an expression for the bandwidth in terms of the circuit components. Certainly, if you know the desired value of C and omega 0, you can find component values that satisfy these equations appropriately. And typically here you do have kind of one free circuit component that you can choose. Maybe again a capacitor. And then you have, once you choose a capacitor value, this equation is going to set your inductor value to give you a desired omega 0. And then once you have your capacitor and inductor, you can choose a resistor value to get your desired value of C. So the bandwidth of this filter which is B, is omega C2 minus omega C1. And that turns out to be simply just R over L. Again, even easier than using the C parameter, we could choose to pick R over L to get a desired bandwidth and an omega 0. We need to figure out how these different terms are related, though. Another thing that you can show, it can be shown that omega 0 is related to the cutoff frequencies. It's actually the geometric mean between the two. And for certain circuits, omega 0 turns out to be pretty close to halfway between omega C1 and omega C2. So another way, instead of using the bandwidth to classify circuits, they may also be classified by what's known as the quality factor, or Q, of the circuit. Q, and that is equal to omega 0 over the bandwidth. So instead of specifying the bandwidth in omega 0, you may see omega 0 and Q specified, but then that directly gives you the bandwidth. And then from our expression for the bandwidth here, we see that the Q would be omega 0 L over R. So a high Q implies a small bandwidth. And so a low Q would imply a wide bandwidth. So, you know, what they would look like, you know, on a dB scale, you know, a high Q circuit is going to look like this, whereas a low Q circuit is going to have a wider bandwidth. It's going to eventually have the same roll off, but high Q, small b, and then this is a low Q, the one with the wider bandwidth. It is true for high Q circuits, and some books use the approximation that Q needs to be greater than 5. I think your textbook uses the approximation that as long as Q is greater than 10, we have a high Q circuit. In this case, we have omega C1 is approximately equal to omega 0 minus the bandwidth over 2, and omega C2 is approximately equal to omega 0 plus the bandwidth over 2. And so you have these relationships as well. Let me save this whiteboard really quickly. We'll continue. I'm not going to actually stop the video because I just want to have one short example and to finish up the lecture. And so let me clear the screen. There we go. And then just do a simple bandpass filter design. So design a bandpass filter with f0 equal to 1 megahertz and Q equal to 20. And then here I'll give you an inductance value to start. And now, again, I've thrown you a bit of a monkey wrench because I'm giving you the frequency in hertz instead of radians per second. And we've got all these different formulas involving these different parameters in our bandpass filter. But typically we'll start with the resonant frequency. That's I'm given L and F0, so I'm really given L and omega 0. So I just want to turn this around and solve for C. I can square this, solve for C, and I get C is 1 over L omega 0 squared, or I have all of those, 0.1 millihenry for my inductance, and then my resonant frequency would be 2 pi times 1 megahertz, and then that's squared. So find out the capacitance I need is 0.253 nanofarads, and then my bandwidth is omega 0 over Q, and the bandwidth might is it going to have Q is unitless, so the bandwidth will have the same units as it may be given in hertz, in which case it would be F0 over Q, or it may be given in radians per second. Again, it's the same value. If B in radians per second would be 2 pi times B in hertz. So here I've already calculated, I know what omega 0 is. It's 2 pi times 10 to the 6, and my Q is 20, so my desired bandwidth in radians per second is actually 2 pi times 50 kilohertz, or 100 pi radians per second by, what am I supposed to say, kiloradians per second. Okay. And then I know that the bandwidth is equal to R over L. Again, L was given, so R is going to be B times L, and then so R here turns out to be 31.4 ohms. And so, my circuit now would be, for this second order bandpass design, with a center frequency of 1 megahertz and a Q of 20. The circuit that's going to meet that design would have, I start out with L is 0.1 millihenries, C is 0.253 nanofarads. Again, here we'd probably use, we'd maybe analyze the circuit in LT Spice using these exact values first, is what I typically do, and then come back and then use the nearest standard component values to see how much that actually affects the design. But at this point you might want to simulate this in LT Spice and see what the frequency response looks like, and then hopefully it's got the desired center frequency and bandwidth or Q. Okay, that concludes all the videos for today's lecture. So hope to see everyone in class as soon as they get the roads cleared, um, and maybe later this week.